Okay, apparently the recording cut out in the middle of the last lecture. So starting over here, I've already finished going through all the slide or the text, so I'll have to highlight as I go to show where I'm at. So diagonalization. If we have that B is a Hermitian matrix, then B equals BH implies that our upper triangular factorization would be the same factorization with conjugated and transposed. Well, since these expressions are the same, except that we've got the Hermitian form of the upper triangular part, then for an upper triangular matrix to equal its own Hermitian, it must be diagonal and it must be real, since the conjugated diagonal terms must equal themselves. So since a real symmetric matrix is a special case of a Hermitian matrix, this applies there as well. So for this, and we're stating some of this without proof, but you can look at the lecture notes, the printed lecture notes, where there are several pages of proofs for how this works. It's just not, although we will do proofs, that's not one I thought was worth the time to go through in class. But VH is also equal to the inverse. That's what it means to have this unitary matrix decomposition here. So that implies that our eigenvector matrices can contain orthocolumns. Well, what about orthonormal? That's what we really like, and in fact it implies that the columns are orthonormal. Well, if we look at our basic eigenvalue eigenvector equation, it's apparent that if we were to come up with a new vector u that's equal to a scaled version of v, then a times u would be equal to alpha a times v, which is alpha lambda times v, which is lambda times u. In other words, we can always normalize eigenvectors. So here are the main properties that we're going to take advantage of quite a bit. And that is first, an n by n Hermitian matrix always has real eigenvalues. Second, and I think this is very, very important, it has n orthogonal eigenvectors. So in other words, the eigenvectors will span the space Rn. Very useful. And finally, if A is real, then the vectors can be chosen to be real valued. In other words, if you come up with something complex, multiplying it by some factor alpha, as we did before, can turn the whole thing real. Okay, based on that, let's go back to this eigenvalue decomposition that we discussed on the previous page. I've displayed it down here as a way to visualize it. The column vector v, which is the first column of v1, which is the first column of v, is always going to be multiplying lambda 1 in this particular scenario. So when we are done with this operation, multiplying v times capital lambda, each column is now going to be the same as it was before, the columns made up of the eigenvectors multiplied by their respective eigenvalues. When we then multiply it by VH, we now are forming an outer product of each of these eigenvectors with itself, scaled by the eigenvalue. So we get this equation over here that I'm circling in red. And this is called the spectral decomposition of A. In other words, A is now a sum of outer products weighted by the lambdas. So